Okay, so we're looking at Chapter 7. This is the mathematics of networks, and Chapter 7 is concerned with solving minimum network problems. Some of the vocabulary that we will focus on in this chapter include subgraph and spanning subgraph. So let's take a moment to work on those two vocabulary words. So a subgraph is a graph made up of parts from a parent graph. And to make a simple example, I have a graph here with 4 points. And as long as I draw a graph using these parts and nothing else, we have a subgraph. So if this is the parent, then a subgraph might look like this. So an example of something that is not a subgraph is here, and it's because of this line segment. That line segment does not exist in the parent graph. It's not here. So we introduced a new part, and if we introduce a new part, then we're no longer a subset of the original parts, and that is why it is not a subgraph. So now that we understand what a subgraph is, we can go and focus on the spanning subgraph. The word spanning means that it must include every one of the vertices of the original graph. So if I were to make a new example here, again, if this is our parent graph, then I can make a spanning graph as long as it includes all of the vertices. So that's a spanning subgraph. Even though I didn't draw any edges, it's still a spanning subgraph because it has all of the points. But now if I start to draw some of the edges in, it is still a subgraph. Oh, there's no line from E to B. I can't include that one. If I drew from E to B, it would no longer be a subgraph. So even though it's disconnected, this is still a spanning subgraph. Now it is a connected spanning subgraph. Connected is not required to be a spanning subgraph. The only thing required is spanning. It must contain all of the original vertices. And subgraph, it must use edges from the parent graph. Our next piece of vocabulary is a tree. A tree is a connected graph with no circuits. So here's an example of what a tree can look like, because everything is connected. But if I put a circuit in there, this is not a tree. So they've provided some examples for us. All four of these, A, B, C, and D, are trees because all of these graphs are connected and none of these graphs have circuits. In this next group, A, B, C, and D are not trees because these first two have circuits in them and these second two are disconnected. Here are the properties of trees which you should read and become familiar with. They are used in some of the sections practice problems to determine if we understand what it is to be a tree. Property 1, if a graph is a tree, then there is one and only one path joining any two vertices. Conversely, if there is one and only one path joining any two vertices of a graph, then it must be a tree. So, how many different ways can you trace this graph to get from A to H? There's only one path there. How many paths exist from A to F? Again, there's only one path that you can follow. If you start at B and end at G, there's only one way you can follow along those paths. That is what property number 1 is saying, that if you choose 2 points, there's only one way you can follow the edges between them. Property 2, in a tree, every edge is a bridge. So, just to recall, a bridge is an edge that if I remove, the graph becomes disconnected. So we see I just removed edge BC, and now I have 2 parts of the graph. It's disconnected. If I remove edge DG, once again, the graph becomes disconnected. Property 3, a tree with n vertices must have n-1 edges. If we look at this example, I'll call it example 1. There are, if you count the vertices from A, B, C, D, E, F, G, H throughout, you have 1, 2, 3, 4, 5, 6, 7, 8 vertices. And if you count the edges, you have 1, 2, 3, 4, 5, 6, 7. This property alone, saying that n-1 edges with n vertices does not guarantee a tree. It is necessary. It is, if you have a tree, this is true, but having this description is not enough to guarantee you have a tree. So let's see what I mean by that. I'm going to erase this down here. If I have 4 vertices and 3 edges, 1, 2, 3, 4 vertices, 1, 2, 3 edges. I created a circuit and a disconnected graph. So having n-1 edges does not guarantee that we would have a tree, But if I drew a tree, it would have to have that the number of edges is one less than the number of vertices. So this is a tree. But being told that I have 4 vertices and 3 edges is not enough to guarantee that a tree would be drawn unless I add a word like connected. Draw a connected graph. With 4 vertices. And 3 edges. Once you say it has to be connected, now I have 4 vertices and 3 edges, it must be a tree. And we've encountered this in previous classes. If you go back to your years in geometry, if we said a shape had 4 equal sides, does that mean it has to be a square? And the answer is no, it could be a rhombus. So when we say a graph has the number of edges that is 1 less than the number of vertices, that's not enough to guarantee a tree. We have to add something more, like it's connected, or that there's only one path joining all of the vertices. We have to add something more to it. So this is a weak condition. And I say it's a weak condition because we have to add something more. And here you see property 4 says that a connected graph with n vertices and n minus 1 edges must be a tree. So they added something more. Property 3 was a weak condition. Property 4 is a strong condition. So here they're going through some of the conditions. If you have a graph with 5 vertices and less than 4 edges, it will always be disconnected. A graph with 5 vertices and 4 edges is just enough to connect. But again, this is the weak condition we talked about. We must add a word such as connected, 5 vertices and 4 edges, and connected, because I can draw 5 vertices and 4 edges, and now it's disconnected. And if we have 5 vertices and more than 4 edges, we see that circuits will always show up, and if there's a circuit, it's not a tree. The next topic is minimum spanning trees. And minimum spanning trees take a graph and connects it with a tree of the least weight. So here's our given graph. And this is our minimum spanning tree. We use MST for that. It is a spanning subgraph that is a tree. And it uses the cheapest edges. So the book gives us a technique called Kruskal's algorithm to construct minimum spanning trees. And if we look at this, Kruskal's algorithm says find the cheapest edge in the entire graph. Well, that's right here. That edge is 42. What's the next cheapest edge in the entire graph? Right there, 45. Next cheapest edge is 49. Next is 51. This 51 I can't use because it would create a circuit. Next cheapest edge is 53. I can't use any of these edges because they would create circuits now. I'm just crossing them out. And what's left is these two edges, and I need to connect El Dorado. 59 is the cheaper edge. I don't need 62, that would create a circuit. So if we take this graph that I drew, this is our minimum spanning tree for the graph we started with here. And they describe the steps in here. And you see that they've drawn the same graph that we did. And they've crossed out these edges with X's, just as we did. Here is their description on how to use Kruskal's algorithm. And that's where we'll stop with this video. So, play the video, take notes, read through the textbook, sections 7.1 through 7.3, and then complete the homework problems I attach.